In November 2016, one of the heaviest buildings ever moved across land began a 327-metre journey. It stood exactly 108 metres high, 162 metres long, and weighed an incredible 36,000 tonnes. It crept forward just 60 centimetres at a time toward the highly radioactive ruins of Chernobyl's Reactor number 4. Stopping halfway was not an option. It would mean catastrophic failure. Just listen to the massive hydraulic jacks pushing this steel mountain forward. How do you build and move a structure this massive without killing the workers building it? To understand why this extreme engineering was necessary, we have to look back at the disaster that started it all. In April 1986, Chernobyl's Reactor number 4 exploded, launching a radioactive plume high into the atmosphere. Desperate to contain the fallout, Soviet workers, known as liquidators, rushed to build an emergency steel and concrete shelter over the smoking, exposed core. Working in shifts that sometimes lasted just seconds due to lethal radiation fields, they hastily assembled this structure. They miraculously finished the original sarcophagus in just 206 days, but that incredible speed came with a severe long-term cost. The hasty shelter was never bolted down or properly sealed. Instead, its massive steel beams simply rested on the damaged, unstable ruins of the original reactor building walls. As the decades passed, the sarcophagus began to rapidly decay. Gaps measuring up to 100 square meters formed in the roof structure. Rainwater poured in, accelerating corrosion, while heavily contaminated radioactive dust threatened to escape into the atmosphere with every passing storm. Inside the crumbling walls sat a ticking time bomb. Roughly 200 tons of highly radioactive melted nuclear fuel still remained trapped beneath the rotting concrete shell. This lava-like mixture of uranium, graphite and sand remained incredibly lethal. If the decaying roof collapsed under its own weight, it would immediately kick up a second radioactive dust cloud, sparking a brand new environmental catastrophe across the continent. Just listen to what the radiation levels sounded like for the few investigators brave enough to enter. By the late 1990s, it was obvious that temporary patch jobs would not be enough to avert disaster. The imminent threat of total structural failure forced an international team of engineers to conceive a massive 100-year replacement shelter. They needed to completely enclose the old sarcophagus so it could be safely dismantled from the inside. But because the space directly over the ruins remained a death zone, they had to build their giant arch completely off-site and then figure out a way to slide it over the ruins. Building a permanent shelter the normal way was an immediate non-starter. Even a decade after the explosion, the radiation field directly above the ruined reactor remained deadly. A construction crew attempting to lay foundations or raise scaffolding directly over the open core would receive a fatal dose in minutes. To protect the workforce, engineers devised a radical plan. They would assemble the new safe confinement 327 meters away. This designated staging area was heavily decontaminated, allowing thousands of workers to operate in standard shifts without extreme radiation exposure. But the physical requirements of the building were staggering. The structure had to completely encapsulate the crumbling sarcophagus without touching it, because it could not rest any weight on the fragile ruins below. Internal support columns were completely ruled out. The only structural shape capable of clearing the entire disaster site was a colossal arch with an unsupported span of 257 meters. Once fully assembled, this massive steel skeleton faced another invisible threat. Natural condensation would eventually rust the metal, but maintenance crews could not routinely inspect or repaint a ceiling positioned directly above a radioactive zone. To solve this, the arch features a complex dual skin design. The structure consists of an outer and an inner shell, creating a massive enclosed cavity between the layers. Giant ventilation systems constantly circulate dried air through this gap, maintaining a relative humidity strictly below 40%. This continuously climate-controlled volume actively prevents moisture buildup and corrosion, ensuring the structure remains safe for at least 100 years without ever needing a human inspection. Even with the staging area safely positioned away from the reactor, constructing a structure this massive introduced a serious logistical problem. The finished arch would eventually stand 108 meters tall, making it far too large for standard construction cranes to handle heavy loads at its peak. To bypass this limitation, engineers devised a plan to build the colossal skeleton close to the ground in two separate sections, an eastern half and a western half. Workers started by assembling the central crown of the arch just above the concrete staging pad. The sheer volume of the steel framework required immense coordination, utilizing over 80 major steel elements that were painstakingly secured by hundreds of thousands of bolts. Once the top section of a half was completed, crews engaged a network of massive hydraulic jacks to push the structure into the air. The site filled with the heavy metallic groaning and clanging of these hydraulic lifts as they ratcheted the thousands of tons of steel upwards in careful, synchronized stages. With the crown suspended, workers built the next vertical level of the arch directly underneath it, bolted the new sections into the main body, and lifted the growing structure again. This bottom-up extrusion method entirely eliminated the need for dangerous high-altitude crane operations. While the framework remained relatively low to the ground, teams also installed the intricate exterior and interior paneling. The arches underwent a striking visual transformation as expansive sheets of gleaming silver cladding were attached, turning an exposed grid of steel pipes and beams into a solid, highly engineered shell. When the eastern half was completely built and fully clad, hydraulic pushers slid it forward along specialized tracks to free up the main assembly zone. The entire lifting and cladding process was then duplicated to construct the western half. Finally, the two fully finished segments were aligned and permanently bolted together, forming a single 36,000-ton megastructure that was ready to be moved into the danger zone. Looking at this colossal steel shell, it is easy to assume its only job is to act as an impenetrable shield. But the arch is not just a static roof, it is a massive mobile deconstruction factory. Hidden inside, suspended directly from the ceiling, is a sophisticated system of heavy, remotely operated cranes. Once the new structure is sealed over the reactor, the decaying concrete sarcophagus built by the Soviets will still be crumbling inside. The ceiling-mounted crane system is designed to carefully dismantle that highly radioactive ruin piece by piece. Giant robotic tools will slice through the old beams and concrete slabs, while operators control every movement from a heavily shielded bunker outside the danger zone. If you are fascinated by the hidden mechanics inside extreme megastructures, subscribe to Industrial Empire. Integrating this robotic dismantling system introduced a severe engineering paradox. The arch had to be robust enough to carry heavy industrial deconstruction machinery tearing into concrete beneath it, yet it had to remain light enough to physically slide across the ground. Every section of the framework had to be precisely calculated to maximize load-bearing strength while minimizing overall mass. Even with these strict weight optimizations, the addition of the crane system and its reinforced support tracks brought the staggering final weight of the structure to over 36,000 tons. Now that the colossal factory was fully assembled and loaded with equipment, the team faced the ultimate logistical nightmare. They had to figure out how to safely push a 36,000-ton metal mountain over 300 meters of track without causing the entire framework to buckle. You cannot simply put a 36,000-ton building on wheels. The concentrated downward force would instantly crush conventional axles and tear through any standard metal track. Instead, engineers laid down two massive custom-built concrete foundations running parallel to the reactor, coating the sliding surfaces with Teflon to drastically reduce friction. To physically push the colossal arch, they installed a synchronized network of 224 horizontal hydraulic jacks. When the system powered on, the exclusion zone echoed with the rhythmic mechanical hiss and deep thud of the hydraulics pushing against their anchor points and resetting. The forward progress was agonizingly slow. Each jack nudged the immense steel mountain in precise 60-centimeter strokes. After every single push, the entire operation had to stop. Automated lasers measured the alignment of the massive legs down to the millimetre before the hydraulics retracted and reset for the next shove. This meticulously controlled pace required over 40 hours of active pushing to complete the 327-metre journey. The environmental and mechanical dangers during this transit were immense. Because of its vast surface area, the arch acted like a giant sail, making high winds a severe threat to its structural stability. But the absolute greatest danger was the risk of skewing. If one side of the structure moved just slightly faster than the other, the steel skeleton would twist, jam on the Teflon tracks, and potentially buckle under its own extreme stress. As the leading edge of the arch finally crawled into the severe radiation zone directly above the exposed reactor, a terrifying reality set in. Human intervention was now completely impossible. If a hydraulic line ruptured or a track warped directly over the decaying ruins, workers could not safely approach the leading edge to perform repairs. The sliding fortress had to cross the finish line flawlessly on its very first attempt. On November 29, 2016, the 36,000-ton New Safe Confinement completed its agonizing journey. The colossal steel mountain slid into its final position, perfectly swallowing the decaying Soviet-era sarcophagus. But simply covering the ruins was not enough. The new structure had to be hermetically sealed against the adjacent reactor buildings. Because the old walls were too fragile to support any additional load, engineers installed flexible heavy-duty membranes. These custom seals moulded against the jagged, irregular concrete of the original ruins, closing off the environment without transferring a single kilogram of weight onto the crumbling facility. Following intense commissioning tests, the structure was officially handed over to Ukraine in July 2019. The immediate impact was profound. The arch completely eliminated water ingress, which had previously threatened to collapse the rotting steel beams inside and carry radioactive isotopes into the groundwater. Simultaneously, it trapped the deadly radioactive dust that constantly swirled around the exposed core. However, the new safe confinement is not the end of the Chernobyl story. The arch did not clean up the meltdown. Instead, it bought humanity a crucial window of time. It created a completely contained, climate-controlled workspace where remotely operated cranes can safely dismantle the old sarcophagus and extract the highly volatile nuclear fuel over the next 100 years. That 100-year lifespan is just a ticking clock to finish the cleanup, not a permanent cure. The site's extreme vulnerability became clear in February 2025, when a drone strike damaged the arch's exterior cladding and internal ventilation systems. Chernobyl is not a finished monument, but an active nuclear safety infrastructure demanding constant vigilance. Thank you for watching. Please leave a comment and subscribe for more deep dives into the world's most incredible engineering projects.